the night sky, we experience directly the result of nearly 14 billion years of evolution of our universe. Cosmology is precisely that branch of physics devoted to study such an evolution. In particular, we want to understand how the stars and galaxies we see today came to be, and crucially, it is necessary to focus on the very first moment after the birth of the universe, a period which we call cosmic inflation. In 1929, astronomer Edwin Hubble discovered that galaxies are moving away from each other, and the further apart they are, the faster they move, which is known as Hubble's law. This was the first evidence that we live in an expanding universe, and the natural consequence is that at some point in the past it must have been very small and dense, a single point in space and time from which everything started. This first instant is what we call the Big Bang. This idea is then accompanied by a fundamental principle in cosmology, namely the cosmological principle. This states that when we look very far, on very large length scales, where galaxies reduce to just single points on a map, the universe is the same everywhere and looks the same in every direction. Mathematically speaking, we say that the universe is homogeneous and isotropic. An evidence for this principle was the discovery, in 1964, of the CMB, a background of electromagnetic radiation originated around 380,000 years after the Big Bang, when the universe became transparent to light. The interesting property is that this background radiation has the same temperature of 2.7 Kelvin independent of the direction it comes from, perfectly resembling a so-called black-body spectrum. However, the highly uniform temperature of the CMB cannot be explained in an expanding universe filled with matter. The reason is that when the CMB was emitted at early times, 2 points far enough in the sky had not had enough time to exchange information and to set to the same temperature. Therefore, a uniform temperature across the whole sky seems to violate the laws of causality. The most convincing explanation for this puzzle is to assume an early period where the universe is expanding very fast, in an accelerated way, a period which is called cosmic inflation. It is believed that around 10 to the minus 37 seconds after the Big Bang, in a fraction of a second the size of the universe doubled more than 100 times. In this way, points in the sky that were initially very close and in causal contact were then sent far away from each other by the enormous amount of expansion. Such a period of inflation is able to explain the uniform CMB temperature. But this is not the full story, since a perfectly homogeneous universe would just stay homogeneous forever, and we would not even be here looking at stars and galaxies. In 1992, small deviations from the homogeneous temperature in the CMB were measured, at the level of 1 part in 100,000. These same fluctuations in temperature are related to inhomogeneities in the matter density of the universe, which are considered to be the primordial seeds for the subsequent structure formation. Under the effect of gravity, they grow larger and larger with time and eventually give rise to the galaxies we observe today. Interestingly, the very same anisotropies measured in the CMB are a direct prediction of the theory of inflation. After the accelerated period of expansion, the universe ended up very homogeneous but with tiny fluctuations on top. The physical explanation for this lies in the quantum nature of reality, which is always in play at microscopic scales but would not affect the universe's evolution in standard circumstances. However, during inflation the universe is accelerating so fast that very small regions are stretched to cosmological sizes. The anisotropies measuring the CMB temperature arise as so-called quantum fluctuations at very small scales, which are then stretched to very large scales by the inflationary expansion. In this sense, the initial state of our universe can really be interpreted as the result of a random quantum process in play at very early times during an accelerated expansion. Along with perturbations in the matter field, inflation also predicts quantum fluctuations in the spacetime itself, which are then stretched to cosmological scales, turning into gravitational waves. This unique signal from the early universe would show up as a superposition of infinitely many incoherent waves with different frequencies. A detection of this gravitational wave background in the future would provide a striking evidence for the inflationary theory.